Now we're going to discuss Green's theorem in the plane. So let's think about what we're discussing first. We're going to allow R to represent a simply connected plane. And I'm going to draw R in the plane. Now, there are a couple things that we want to notice about this region R. The boundary must be a simple closed. It can be piecewise, but it must be a smooth curve. And of course, it's oriented so that we are traveling in a counterclockwise direction. So counterclockwise, oriented counterclockwise, or a positive orientation. Sometimes it's hard to see, but one way to think about it is that as you are traveling along this boundary, that the region is on your left. And the reason I specify to think about it as having the region on your left as you're traveling in that counterclockwise direction is because sometimes you could be dealing with a space curve, it could be turned on its side or in a different shape, and it might be hard for you to determine or ascertain which direction is going to be counterclockwise, but counterclockwise is important. And if my components m and n are continuous and they also have continuous first partial derivatives on this open region or the set containing R, then what we can say is this line integral in the directed counterclockwise direction of f dot t ds. So this is just our typical line integral, and we now have this circle, this directed circle, which indicates we must be talking about a counterclockwise rotation. So our typical line integral can be defined as that directed integral of m of xy dx plus n of xy dy, or rather the double integral over R of partial n with respect to x minus partial m with respect to y, dA, which just means dx dy. So you'll notice here, this is my definition of curl, and we call this just our curl integral. And essentially what we are stating using Green's theorem is that we can turn a line integral into a double integral over the region R. Green's theorem applies to any vector field, independent of our interpretation of the field. Now, this is the Green's theorem form for circulation density, or the curl form, but there's also a Green's theorem for flux or divergence. So restating what this integral says, it's the counterclockwise rotation of a vector field around a simple closed curve. Simple just means that there are no twists or overlaps in it, and that this is now equal to the double integral of the k component of the curl, which is what this is. We just learned how to calculate that, of the field over the region enclosed by the curve. So we have a second form of this definition. So this form that we're looking at here, part A, we'll call that A, is related to the curl. We also have a flux form, and that essentially says the same thing, that line integral, the directed counterclockwise line integral of f dot t ds, which was our definition for work, this can be represented as the line integral over c. I left my c's off up there, but the line integral across c of m dy minus n dx, or rather the double integral over r of partial m partial x plus partial n partial y dA. So in here, this tells us about flux or divergence, which we have not talked about yet. But if you were asked to count, or to calculate, I should say, outward flux, then you would solve this double integral using your divergence or flux formula. And let me pull in the definitions from the text because those just look a little nicer. They have more words. You can pause and read it and write more. So here we see how we calculate circulation density, and we see that showing up over here in my curl integral. So essentially, if you are asked to find the counterclockwise circulation of F around that curve, that bounding path, which is enclosing essentially a loop enclosing R, then that would be the same as calculating the double integral over R of the curl. Similarly, the flux or the divergence, which is a measure of the expanding or compressing at each point, we can calculate that divergence or flux density using partial m with respect to x plus partial n with respect to y. And so if we were asked to find the outward flux of F across the curve C, that would equal the double integral over the region R of this flux or divergence calculation. So flux is the amount of something passing through a surface, like an electrical field, whatever you want passing through a surface. So that's what flux is. And then divergence is the flux density or the flux per unit, or rather essentially the amount of flux entering or leaving a point, the rate that the flux is expanding or contracting. And essentially the point of all this is that Green's theorem gives us a really easy way to calculate both the outward flux or the counterclockwise circulation. So I'm just going to verify for us that one of these two theorems is true. We're going to look at the circulation density theorem, and I'm going to show you proof form why this is true. In this example, we are going to verify or prove that Green's theorem, the curl version, holds for this vector field F, which is equal to x minus y I plus xj, over the region R, which is bounded by this unit circle given as cosine ti plus sine tj, traveling counterclockwise from 0 to 2 pi. So essentially what we're being asked to prove is that the directed line integral across C, or along the curve C of f dot t ds, is equal to the directed line integral C of m dx plus n dy. And we want to show that that is equal to the double integral over R of n sub x minus m sub y dA. So we essentially just need to show here that the integral on the left, that directed line integral along the curve, is equal to the double integral on the right. So I'm going to start with the left side, and we're going to evaluate the counterclockwise circulation of F around the curve C. So in order to evaluate that line integral, we first need F in terms of t. So F of R of t, well, that is going to be cosine t minus sine ti plus cosine tj. At this point, I know what my m and n values are, I just need to take the derivative of x and the derivative of y. So I'm going to set this up here. This is going to be the integral from 0 to 2 pi m, I have cosine t minus sine t. The derivative of x, that's going to be negative sine t, plus n is cosine t, and my dy value is going to be cosine t dt. So that's the integral from 0 to 2 pi of negative sine t cosine t plus sine squared t plus cosine squared t dt, and sine squared plus cosine squared is going to give us 1. So this is the integral from 0 to 2 pi of 1 minus sine t cosine t dt, which we can integrate the first term using the power rule. I've got t, the second using u sub, which gives me 1/2 sine squared t, evaluated from 2 pi to 0, and everything except that very first 2 pi is going to cancel out, so we get 2 pi. Essentially, what we've just shown is that the left side of this equation is equal to 2 pi. So what you're going to see is that when I calculate this for the right side, it's going to be a much shorter computation. So looking at the right side, I do not have to deal with parametrizing it and setting up that composition. I just need to know what m is. M is x minus y, n is x. Partial of m with respect to y is -1, and partial of n with respect to x is +1. So if we set this up, my double integral over my unit circle region is going to be n sub x, 1, minus m sub y, -1, dA, or 2, the double integral over that region, dA. This double integral will be calculating the area. The area of a unit circle, or a circle of radius 1, pi r squared, pi times 1 squared, is just pi, and we get 2 pi. There you have it. We proved that Green's theorem holds. Or rather, we verified Green's theorem, the curl form of it, for this vector field over the region bounded by the unit circle. As always, feel free to send me emails, questions, concerns. Get in touch with me if you need help, because that's what I'm here for.